Welcome to 35th lecture in the course of Industrial Engineering and Operations Research. Now we are discussing very important topic of operations research, that is linear programming, and I already told you two methods of solving linear programming problems. One is graphical method and other method is simplex method. In the simplex method, I told that how to make simplex table, and basically we do a type of Gauss-Jordan type of operation and then we get a solution. In that also I told two methods, that big M method and two-phase method for solving linear programming problem using simplex method. Big M method and two-phase methods are needed when you have constraint which are of equality type or which are of greater than or equal to type of sign. In that case, we do not get any convenient way to choose a basic feasible solution. That is why we have to introduce artificial variables and then go ahead with that. Now today I am going to discuss some special problems in linear programming. Many top problems you can practice from the books, okay, such as books by Taha and books by J.K. Sharma. Many other books are there. Also you can get lot of practice problems from the internet, but I will discuss few special type of situations which arise in the linear programming, and by that way it will be little bit revision also to you. So one thing is that I want to tell you degeneracy. What do you mean by degeneracy? That when one or more of basic variables are 0. So let me remind you again that what do you mean by basic variables? Say for example, if you have x plus y plus z is equal to 10 and you have another thing 2x plus y plus 3z is equal to 27. Now you have got these two equations, but you have got three unknowns x, y, z. So obviously you cannot get a unique solution. You will have many solutions because you can keep putting various values of, say, you can fix one thing because two equations, two unknown can be easily solved, okay, but two equations and three unknown you are not able to solve. You can solve only that suppose you put some value of, let us say, of z, and then you get and solve for remaining x plus y is equal to 10 minus z, 2x plus y is equal to 27 minus 3z. If you solve that, you will get some solution. So that way, by putting different values of z, you can get different values of x and y. Similarly, you can fix x also at some value. So how many solutions are possible here? Basically, there are infinite number of solutions possible, but we do not call them as basic solutions. Basic solutions are that suppose I force that z is equal to 0. So z becomes non-basic, then I am left with two equations, that means x plus y is equal to 10 and 2x plus y is equal to 27. Then I can solve these two things and I can get a solution by solving that whatever value I got a x and y that I have taken, and along with that z becomes 0. So this is called, x and y will be called basic and z will be called non-basic. Similarly, I can obtain another that basic solution. How I can obtain another basic solution? I can put x is equal to 0. So then y plus z is equal to 10 and y plus 3z is equal to 27. So I can solve these two and I can get another basic solution. In this basic solution, non-basic solution will be x is equal to 0. So x is equal to 0 will be non-basic, okay, and y and z something will come that will be basic. So I got another basic solution. I can get even a third basic solution also, that I can put y equal to 0. So I can say x plus z is equal to 10 and this is equal to 2x plus 3z is equal to 27. So so either I can put x equal to 0 or I can put y equal to 0 or I can put z is equal to 0. So whichever is I am putting 0, that is called non-basic, and remaining variables are called basic. Okay. So that way I can, so here there are only 3 possibilities. So that's why 3 possibility, because I can make one non-basic variable 0. So 3c1. 3c1 is basically 3. Or I can say I can make 2 basic variables, only either xy or xz. So it is basically 3c2. So 3c2 is also same as 3c1. So that means this way you get a finite number of solution. So what I said, that variable which becomes 0, which I force it 0, that becomes non-basic. Then for basic variables I have to solve the equation. But my assumption is that they can take any value, but it may so happen that basic variable also may become 0. So if basic variable becomes 0, that situation is called degeneracy. That means we have got degenerate basic solutions. So when one or more of basic variables are 0, this is called degeneracy. If one or more of the basic variables in a basic solution has value 0, this solution is said to be a degenerate basic solution. That solution is called degenerate. In simplex iterations, it may keep going on without changing the value of objective function. It is called cycling. So that means, what is the consequence of that? If you get this type of situation, your simplex method may keep moving on. I have already solved 1 or 2 problems in which you saw that some coefficient was 0, and I said let us introduce this also, but you got the same objective function, no change in that. So basically you can say energy level remained same, but unnecessarily it has to be cycling. So why sometimes if you do not have provision to terminate, if you do not understand that situation, then it may keep going on. So some people have also suggested some methods that how to remove this problem, but many packages do not incorporate that feature, because such type of problems occur very occasionally, and they may say that okay fine, that means one can understand that if it is cycling too much, if taking more time, then of course it can be this one. So let me understand by that one method that which I have solved by this one, but solution using simplex method, and with the help of open access online solver, I tried to solve this. Maximize z is equal to 2x1 plus 6x2 subject to x1 plus 4x2 smaller or equal to 12, x1 plus 2x2 smaller than 6, and x1 x2 greater or equal to 0. You can solve this problem by using math-a2z.com also, and but anyway it is very easy also. Problem is this, and I have written it like this. Now here the constraint is of this type, smaller or equal to type of thing. So I can introduce the slack variables. It is very easy. I need not use even big M method. I don't need not use two-phase method. It is very simple because it is smaller than equal to type. So I just change that right in the standard form. I say x1 plus 4x2 plus s1 is equal to 12. Because it was less than 12, so I added plus s1. Then x1 plus 2x2 plus s2 is equal to 6. And x1, x2, s1, s2 greater or equal to 0. In the coefficient, in the objective function, I have written 2x1 plus 6x2 plus 0s1 plus 0s2 because they have been added. They are slack variables. They do not contribute to cost. Now, how can I solve that? This method can be done by simplex also. Usually I have told that in which z row I write on the top, but you know that in some packages you may get like in the bottom also. So that's why I am just retaining that, so that you should be able to understand if you get any type of thing. So here I am telling that what we are calling z row and which I used to keep in the top, it is kept here. It is -2, -6, 0, 0, because -2 means coefficient of x1. minus 6 means coefficient of x2, s1 0, s1 coefficient is this one. And then as I said that starting basic solution is what? S1 is equal to 12 I will take, okay. So that means S1 row I will write, this is 0, this is, and this is 12, okay. That means this value, that because that is right hand side value 12, right hand side here is written in the left side, x1 is equal to 1 and x2 is equal to 4, s1 is equal to 1, this is 0, and then s2 is equal to 6, that is the solution, basically solution which I used to write on the right hand side. This is 1 2 0 1, and that's all, and z is equal to 0, zj value has been also written, okay. Ignore that now at this moment. Now we find out, so what should be the my entering variable, because most negative coefficient, because it is a maximization problem. So minus 6 is becomes the entering variable, then that becomes the pivot column. So we divide 12 divided by 4, that coefficient in S1, coefficient of x2 is 4, so 12 by 4 is 3. Similarly, you do 6 by 2 is equal to 3. So in this case, both have become equal, okay. So that you understand that this is a type of situation that which may cause you degeneracy, because most of the time both the ratios have. So which one to go that? So negative is minus 6 and its column index is 2. So the entering variable is x2, minimum ratio is 3 and row index is 1. So suppose I say, suppose I make leaving basic variable as s1. Even I can make s2 also, but I have to choose one. So entering x2, departing s1, and key element, that means pivot element, becomes 4. So first thing is what? That R1 new means R1 old by 4. That means whole thing has to be divided in that row by 4, so that it becomes normalized, and coefficient of x2 which will come here will become 1. And then R2 new means R2 old minus 2 R1 new. That means here in the second constraint you have to multiply whole thing by 2 and subtract in the S2 row, so that this becomes 0. So this procedure has to be done. So in iteration 2, basically you have done this type of situation. So you got 12 and you got S2 is equal to 0, and similarly you modified your row also, Z row also in the same way. Then you got here minus 0.5. So now negative minimum is basically minus 0.5. So that means entering variable still can be x1. Now minimum ratio, if you calculate that here in that way, so you got one place 12, but other place you are getting 0. Hence entering variable is x1, but departing you have to take minimum is 0 only. So you can take this one, and notice that at this stage your optimum function value is 18. So you do that operation and you say that I decide that entering is x1 and departing variable is s2, and R2 new you found that R2 old divided by 0.5, because you have to normalize that. So in the pivot element was 0.5. So you whole thing you divide by 0.5 and you get this one, and R1 new is equal to R1 old minus 0.25 R2. That means in that pivot column all the coefficients will be made 0. So that row operation you have done, and so after doing that, what you got? You again got the optimum value is 18. That means no improvement took place, but you had to do one just unnecessary, that one more iteration, and value you got what? Earlier also you got earlier you got in this solution you got x2 is equal to 0, because x2 is equal to 0, and yes, and you got not x2 is equal to 0, x2 is equal to 6 rather you got. And what was your objective function? Objective function is this one, 6 into this one, okay. So x2, no, this was s1, this was s2. So this is iteration 1, okay. Let me go to iteration 2. In iteration 2 you basically got xb, that means this is the xb row, this is that one, okay. So this is the solution row. So basically you got x2 is equal to 3 and you got s2 also is equal to 0 some value, but since x1 is not there, that means x1 is equal to 0. So second case also you got basically the same type of thing. in the second case, okay, second case also you got x1 is equal to 0 and x2 is equal to 3. Only thing that now it is in the table. Earlier x1 was non-basic, because of that it was 0. This time it is basic, and because of this is 0. But ultimately it is same, and you unnecessarily you have to do 2 iteration. You see, if you solve this problem slowly, you can pause your video, you can practice yourself. You can see in iteration 1 you have got the value objective function was 0, because I put x1 x2 both equal to 0, s1 s2 are the basic. The second iteration I got 18 function value, and in the third also I got 18. So I had to do this one, and this is a very simple problem in which only 2 variables are there. Imagine there are 1000 variables, and if this type of situation occurs, you may have to do many iterations and it will keep cycling. So this problem is called cycling, like in a cycling. So this is the thing that it may happen. So I am making you aware about that. Now let us see graphically what is happening here. So graphically it is like this, that if I have got 2 constraints, okay, one constraint is x1 plus 4x2 is smaller or equal to 12, x1 plus 4x2 is smaller or equal to 12, x1 plus 4x2 is smaller or equal to 12. This is one constraint, okay. Other constraint is what? Other constraint is x1 plus 2x2 is smaller or equal to 6. x1 plus 2x2 is smaller or equal to 6. So how to do that situation? That here if I plot that one constraint x1 plus 4x2 is smaller or equal to 12, that means in the graph paper I can put this equation x1 plus 4x2 is equal to 12. Now when x2 is equal to 0, x1 becomes 12, so I got 1 point, and when x1 is equal to 0, x2 is equal to 3, I got another point, and red line has been drawn. This represents your constraint x1 plus 4x2 is equal to 12, and you have to be less than this one, so means you have to be this side, okay. And then what happens? The other one, x1 plus 2x2 is smaller or equal to 6. So that means if x2 is 0, x1 is equal to 6, you got 1 point, and similarly you will get another point that when x2 is equal to 3. So you join these two and you get a green line, and this is saying x1 plus 2x2 is smaller or equal to 6. So you see that what type of situation you are getting, that at this cardinal point you are many combinations are there. That means here it is okay that you know that one constraint is cutting another constraint, because x1 greater than 0 is also constraint, and similarly here one constraint is cutting, but here there are two constraints are meeting at one point. So basically we can say 3 constraints are meeting at this point, okay. So when this type of situation comes, naturally that this becomes a case of cycling, because the algorithm may confuse that you know it goes from kernel to kernel, but here also, here in fact there are 2 kernels merged at one point, okay. So anyway, this type of thing is there. Now I am discussing another case, a case of alternative optima or infinite solution. Already we have discussed that, but to reinforce it, I am taking another example. So you see objective function maximize z is equal to x1 plus 2x2 subject to constraints 2x1 plus 4x2 is smaller or equal to 8, and 2x2 is smaller than 10, and x1 greater than 0, x2 greater than 0, non-negativity. You see, carefully I have chosen a problem for you just to explain that where if you see it carefully, your objective function is x1 plus 2x2, but the constraint is 2x1 plus 4x2 is smaller or equal to 8. So just you multiply objective function by 2, you get left hand side of the constraint 1. So that means and it should be less or equal to 8. So that means your constraint line, suppose it is a constraint line here in the graph, suppose this is the graph, and objective function line both will merge on each other. As we used to say that now, we used to find out for this distance, then you know with the help of mini drafter I used to draw a parallel line, and that parallel line will touch a extreme kernel, but here since it is a line, so it will merge on that. So you will have not a kernel, but you have many solution. So this type of situation will be there, but even then let us do by simplex. So 2x1 plus 4x2 plus s1 is equal to 8 and 2x2 plus s2 is equal to 10 and x1, x2, s1, s2 greater than 10. And if we solve that, so we make that initial simplex table. It is the same way here, z row instead of top I have written in the bottom -1, -2, 0, 0 and s1 is equal to this, and new table after pivot operation. So that means I have done this one. So after doing this, so we have written x1, x2, s1, s2 and we have found that z value is equal to 10 and we got one solution after solving that. X2 is equal to 2, s2 is equal to 0, 6. So you don't have to put in the objective function. X1 you can say 0. So this is the objective function was what? X1 plus 2x2. So therefore its value is 4. Alternate table also you are getting that you are getting x1 is equal to 4 also as a solution, and x2 will be obviously 0. S2 is there, but you don't bother about x2. So basically you have got two solutions. One solution is that solution A, because your objective function is, I am writing it again. What was the objective function? I am writing it again. Z is equal to x1 plus 2x2. Z is equal to x1 plus 2x2. Okay, I am putting it like that. So solution A, here I put x1 is equal to 0, x2 is equal to 2. So you get z is equal to 4. And if I put x1 is equal to 4, that is also feasible, and x2 is equal to 0, I got another solution. So these are the two kernels, no doubt. But then you can get infinite solutions. How you can find out that? So it is like this, that if you say lambda times, okay, I can have 4 0, that means solution B, plus 1 minus lambda times 0 2. Okay. So therefore what happens that this becomes 4 lambda and this becomes 2 1 minus lambda. Okay. So and lambda is between 0 to 1. So you can get infinite solutions here. Okay. Let us take one case of unbounded solution. Okay. So unbounded solution means, suppose I am giving the situation maximize z is equal to 15a plus 20b. Okay, I just have written the final thing in standard form. Actually the problem is something maximize z is equal to 15a plus 20b. Okay, that was this one, 15a plus 20b. Okay, 15a plus 20b you can see, and subject to 2a plus 2b, a plus 2b greater or equal to 10. Suppose I say like that, and then I say 2a minus 3b smaller or equal to 6, and then I say a plus b greater or equal to 6, and then I should say ab greater or equal to 0. Both are positive. Okay. So first one, a plus 2b greater or equal to 10 has to be written a plus 2b minus c is equal to 10. Is equal to 10 because c becomes surplus variable. Okay, because it is greater than this one, so some extra thing has to be subtracted, minus c. But then plus r1, I introduce one artificial variable, because I said that wherever we will get equality r greater than, then I will put that artificial variable, that is r1. And 2a minus 3b smaller or equal to 6. So no problem, 2a minus 3b plus d, d is the slack variable, and a plus b greater than 6. So a plus b minus e is equal to 6, but introduce artificial variable r2 and say a, b, c, d, e, r1, r2 greater than 0. And now by solving it big M method, you can use m is equal to 100. Okay, 100 is much bigger than 15 and 20, so you can use that. And now I am using that basis, no, not basics, it is basic, and a, b, c, d, e, r1, r2, like that you have written. There is no need to write z column. Okay, that is hardly of any use, but some people write that also. So Z row means minus 15, minus 20, 0, 0, 100, 100, 0. R1 means 1, 2, minus 1, 0, 0, 1, 1, 0. And then D means track variable is D. So D is equal to 2. Coefficient of A is 2, coefficient of B is minus 3, like that. And here R2 also I have written 1, 1, 0, minus 1, 0, 1, 6. Okay. So starting solution is basically R1 is equal to 10. R1 is equal to 10. This is the basic solution. D is equal to 6 and R2 is equal to 6. These are artificial variables. That's why we have added. Now this is not consistent, because if R1 is equal to 10, but you see my maximization is Z is equal to 15A plus 20B, but I want that R1, R2 should become 0. So I subtract minus M times R1 minus M times R2, so that in the process of solving it, R1, R2 becomes 0 automatically, because M is a big number. So therefore what we have to do, that if I use this objective function, we see that R1 is equal to 10, D is equal to 6. So objective function should give me minus 16M, but here it is 0. So that means this is not consistent. So what we have to do, that multiply R1 by 15 and add in this, and similarly you multiply this one. So minus 15 and this is this one, and similarly multiply R2 by this one. R1 is equal to 10 basically. R1 is equal to, here you are getting 10. So you can multiply it by 10. Okay, this row you can multiply it by 10. And R2 is equal to 6. So that means you can multiply it by 6 and you can add in that. Okay. So therefore what you do that, so then it will become consistent. Okay. That means 10 into this one. So basically it can be multiplied by, rather you can say not by 10, you multiply it by M. Okay, by M. Okay, MR1, this is by M. So that means 10, suppose you multiply 10M, 6M. So here it will become 16M, but like that everywhere it will go. So I am taking M is equal to 100, so it will become 1600. So what will happen, let me go to this, becomes minus 1600, solution becomes minus 1600. Okay, minus 1600, no, it is basically not minus 600, you have to write plus 600, this is plus 1600, and you do that here, you have to do that if you multiply it by M, so minus 15 and this one, and you multiply by 10 and into 16, so this becomes this one, so you will get this one, and this problem is of this one. Okay, let me just go to that slide again, maximization problem. Okay, so fine. So therefore what happens, that next one you get okay, minus 215 and this is equal to this one. So you get and you do that operation and you do that one. So what happens, that in that case, suppose the most negative coefficient is actually coming, in fact there is one column that where all the values are becoming, suppose, negative. Okay, that means this is half and this is the thing. So okay, so this is becomes a unbounded type of solution. Okay, if you get like that, so Z is equal to this one solution and D is equal to 21 and R2 is equal to this one. So what may happen if you encounter that type of situation, that you will be getting one column, okay, in which you will be getting all, that means there may be some entering variable, but there is no leaving variable, because everything will become negative. So that means that type of situation can be called unbounded solution. Okay, I am have not completed it fully, but you can complete it and you can ascertain that how it will be there. Okay, and then finally let me discuss alternate this one, initial case of alternative, no, it is going backward, let me just put in the front, infeasible solution type of thing. when artificial variables do not become 0. So that is the situation, that suppose z is equal to 2a plus 5b subject to 3a plus 2b greater than 6, 2a plus b greater than 2, ab greater than 0. So maximize z is equal to 2a plus 5b minus 5r subject to that you 2a 3a plus 2b minus c plus r, and this is a plus b plus d is equal to 2, and here also I put a large penalty and for artificial variables, and then we get this one. So okay, it is going backward, it should go in front. So I keep solving that and I got to many iterations, but finally I am still getting the solution in which r is remaining. So if r is remaining, that becomes it is infeasible solution. Okay. So that means what is the type of thing? Let us see it graphically why it is becoming infeasible, because it is maximized z is equal to 2a plus 5b and subject to 3a plus 2b greater than 6, 2a plus b greater than 2, ab greater than 0. So if you plot that constraint, this is 3a plus 2b is equal to 6. Okay, so a is equal to 2. So this is that one line. So that means it says that feasible zone has to be this side, but other constraint is 2a plus b is smaller than 2. So it says that it has to be this one, this side. So you see that it is not able to satisfy. There is no point. If you put a point here, it will violate this constraint. If you put a point here, it will violate this constraint. If you put a point in between, it will not satisfy both the constraints. So it is naturally infeasible. Graphically we can see, but in the simplex method how it will come, you will not be able to eliminate the artificial variable, and in the unbounded solution what happens, you will encounter that type of situation that you will have some entering variable, but you will not be able to take any leaving variable because their coefficient may be negative or 0. So either it will become infinity or it will become minus value. So there is no, you have to take least, you have to see least comma ratio, but least ratio will not come. So this is the thing. So it is in fact, if you ever encounter a type of table, whether it is entering variable or not, even if there is some variable which can be possibly entering, that suppose x1 is there and x2 is there. Let us say x1 coefficient is minus 3 and x2's coefficient is minus 5, and suppose so therefore you have to take out x1 can be entering variable because it is the greatest negative coefficient in maximization problem, but it is possible that here that may be in associated pivot column terms may be 2, 3, 5, but in minus 3 it may be minus 1, minus 2, minus 3 type of situation. So you can yourself see that even though x1 is not the entering variable, but even if it's all the coefficients in that pivot column are coming negative, so that means the problem is unbounded. So there itself you can stop. Otherwise you will keep doing that thing, one iteration you can do and x2 will enter, but later on you will get that type of situation. So this is the thing which has to be understood. So these are the problems which I have explained today, and then we will discuss the next things in our subsequent lectures. Okay, fine. Thank you very much. Okay.